Okay, so today our speaker is Oren Ben-Bassat from Haifa, from the University of Haifa. And the title of his talk is the Ind-category of Banach spaces. Please.
Okay, Alexei, thank you for the invitation. So, um, I'm going to be talking about Banach spaces and this Ind category, which is kind of alternative to the world of topological vector spaces. Um, and I'm going to start with kind of a abstract philosophy. It's due to Deling and other people, but the idea is that if we start with a monoidal category, we can make sense of rings in that category. And if we start with a symmetric monoidal category, we can make sense of commutative ring objects. Also, please feel free to stop me because I don't have like a huge amount of slides, so I'm happy to stop. Um, so a typical example is the category of vector spaces over a field. And I'll always be using this F symbol to be the reals or the complex numbers. And um, if we're working over a field, there's not so much homological algebra in this algebraic situation. So the tensor product, it's left and right exact. And we, of course, have the vector space of all homomorphisms between two vector spaces. And the whole category, you can kind of build it up from finite dimensional vector spaces. So I can take, I'll discuss this in construction more, but this is basically saying that you can think of a vector space as a union of its finite dimensional subspaces. And the finite dimensional ones are compact objects or dualizable objects, and you have an abelian category. So it's a closed symmetric monoidal abelian category. Um, and F algebras are just commutative monoids or unital commutative monoids in that category. So I don't want to go into the details about symmetric monoidal categories, but they include this kind of bifunctor of two variables. In this case, it's just the tensor product, and they have um, natural transformations like so V tensor W is isomorphic to W tensor V, and there's all kinds of compatibilities and associators and units, all kinds of units. But intuitively, you're just working with vector spaces, like all the things that we can do with vector spaces. Um, And if you have an algebra, you have the category of modules. Again, it's an abelian category. And the affine schemes are just the opposite category of this category of algebras. So I wrote com of vect op. And when you're dealing with affine schemes, you want to sort of glue them together or glue together objects over them, such as like vector bundles. So you need some notion of closeness among points. So you or you need some notion of when something is local. So usually this is encoded through a growth-ending topology, and like the Zariski topology um, has these kind of covers in it, where I localize the ring by inverting some elements Fi, and we take this finite collection of elements that so that the identity is contained in the ideal generated by them. And those are our covers. And then there's a long history, like people like Rosenberg um, Savage, I think, many other people in trying to relate categorical properties of this category of modules to geometric properties of algebraic geometry. So people like to rephrase things in terms of either the abstract category of modules or the category of rings and try to see what kind of things can be defined, not sort of ignoring the fact that they're modules or ignoring the fact that they came to you in some specific way and just looking at them as categories. Also, homological algebra, the whole notion of an abelian category is kind of just modeled on categories of modules, but it, you could think of it in some other way. It could be some other kind of abelian category. And you sort of ask what kind of geometry can you do? So um, I want to remark that instead of just inverting single elements the way I did, or finite numbers of elements, you could invert even possibly infinite subsets. And so you can localize a ring at some kind of infinite subset. For instance, if I take the polynomials, I can invert uh, these x minus si, and so I'm getting um, all kinds of interesting poles in the kind of functions I look at. And like a lot of people in the seminar have probably seen this homological epimorphism property. And this is in fact satisfied by these localizations. So I should say that the category of modules has enough projectives or so we can make sense of derived tensor products. Any questions? So now, because this is an analysis seminar, I don't want to look at, I want to look at a different symmetric monoidal category. So let's just look at Banach spaces over the field. Uh, and I'll use this projective tensor product because it's a right exact functor in each variable. And the projective tensor product is defined as this completion of the algebraic tensor product with respect to this semi-norm. And the semi-norm is just you take all possible ways of writing your vector u, which is an element of this, as a finite sum. And for each of those ways, you get this real number, the sum of the products of the norms, and then you take the infimum over all of those. And so the important operations in this category are like kernel, but the kernel is just the kernel. It's a closed subspace. It inherits a Banach structure, and the co-kernel, which is um, not the same co-kernel from algebra because you need to get something complete. So you mod out by the closure of the image. And you say that a morphism is strict. Sometimes this might be called admissible, but I'll just use the word strict to make sure that what I mean. It's strict if there's an isomorphism of Banach spaces between the co-kernel of the kernel and the kernel of the co-kernel. And the right exactness that I spoke of is related to the existence of this left adjoint, which is the internal hom with the operator norm. So in this case, this is the left adjoint to tensoring with V is to hom from V in the other variable. And it's a quasi-abelian category, which is a certain type of exact category where the Quillen exact structure is given by the strict monomorphisms. So monomorphisms just being a categorical notion, and the strict epimorphisms. Now, some important properties of objects in this category are flat objects. And that's an F, so that tensoring with F preserves strict monomorphisms. And projective objects, meaning that Hamming from a element P um, takes strict epimorphisms to surjective maps. And in the usual way, I mean, of course, F itself is projective, and uh, so is uh, so is any oh sorry yeah, okay, so that's projective and flat, and sometimes we use like an auxiliary category to construct certain objects in the original category. And that's so in this bond category, the objects are just sort of, I mean, the morphisms are just F-linear maps that are bounded in their operator norm or continuous, uh, which is the same as continuous F-linear maps. But um, but now in this contracting category, you only look at morphisms with operator norm less than or equal to 1. And unlike the Bon F, this contracting monocategory is closed under limits and colimits. All right, unlike Bon F. And here's classical objects from functional analysis in Banach, classical Banach spaces actually appear as colimits or limits in this contracting category. For instance, L1 is just a colimit in the contracting category. Okay, so this is if you order the elements of S, say that S were countable and you order the elements, this is just the usual L1. I've added some weights here. So I'm going to use the notation. Okay, so I'll use the notation in this talk that F R, where R is between 0 and infinity, is just F, but the norm is the norm of an element is the absolute value or usual norm in the complex numbers of that element times R. So it's just a weighted version. And this thing is projective, and Von F has enough projectives, and this thing is injective, and Von F has enough injectives. But the the injectives don't seem to be very useful, even though they exist here. Yeah, there's some in other settings they don't seem to exist, so there's a problem with that. But it is possible to prove that there exist non-projective or even not flat objects in Bond F. So this is a nice category from the categorical perspective, especially once we add limits and co-limits, which we're about to do. But it's a strange category because even though we're working over a field, we have homological algebra. We have non-zero X groups and non-zero Tor groups already showing up. So that's a little bit strange. I don't really know what those things mean, but they do exist. Probably maybe Alexei knows more than me. Uh, sorry, I mean, but the thing is, in topological vector spaces, those you don't have those at all. So in topological vector spaces, I mean, you still have the I mean, yeah. For instance, you have the Hahn-Banach theorem, so you don't have like X groups, but here you can have not higher X groups, and I think Tor groups I'm not sure about, but so. we usually compute these TORs or these derived tensor products using projective resolutions. I'll give some examples in a second. And
So can I ask a question
sure.
concerning this one? So your morphisms in Bond, are you accepting like strong morphisms again?
No, all morphisms, all
Ah,
continuous morphisms are bounded
oh,
morphisms.
oh,
So I
okay.
only, yeah, I only defined strict morphisms because I wanted to explain what this Quillen exact structure is. But the category has all bounded morphisms.
Okay, okay. But in Bond, all should be less than or equal one, right? Did you accepting just
Yeah,
contractions?
yeah. So there's the category bond less than or equal to one, where you take uh, F linear maps
Yeah.
whose operator norm is less than or equal to one, and there's bond itself where you're taking any operator norm that's finite.
Okay. But how are you defining the resolutions, all the torsion groups, all the
Yeah, so the main thing we work with is projective resolutions, and those are enough
okay.
to define X and Tor groups. But injective resolutions you can also do, but it's I've never found that useful. I mean, in any way.
Okay, okay, good. So the projective resolution is just you accepting just exactness, right? Exact. That's it.
So the projective resolution has to be strict exact. So
I speak to exact. Oh, okay,
yes,
okay. Yeah, I
yeah,
got it. Okay, thanks.
sure. I mean, yeah, you need strict epis from projectives. Okay, so now, except for the injective resolutions, you can just mimic this, all these properties, if instead of working over the field, you're working over an F algebra. So, except for anything about injective resolutions, nothing changes. It's still a quasi-abelian category. It's still symmetric monoidal. It's still closed. It still has enough projectives. Basically looks exactly the same. Um, and so also if A is an F algebra, I mean, I meant a Banach F. I meant to say a Banach F algebra. If A is a Banach F algebra, you have the exact same properties kind of inherited from Banach spaces, and it's easy to define the projective tensor product over A, etc. So let me give an example of the kind of uh, so I should say in algebraic geometry, you usually work with finite presentation. So you usually work with um, these categorically compact generated things, which they're just polynomial algebras, and then you take quotients and maps between them. So here, I'm going to look at the disk algebras. Now, you can say, I mean, they are kind of categorically defined because this is a symmetric algebra, which is a adjoint functor to the forgetful functor from algebras down to just F vector, I mean, F Banach spaces. But I've written this less than or equal to one because this is like the symmetric algebra as an adjoint from Ban less than or equal to one and of well, so the symmetric algebra, it's like you take okay, so in usual algebra, the symmetric algebra is like V tensor n mod Sn, and you take the sum over all n. So here I'm taking the coproduct in the contracted category. And what you get is an L1 disk algebra. Okay, so I'm going to denote it by x1 So there's going to be these radii involved, R1 up to Rn. And what this thing is explicitly, well, it's as an algebra, it just lies somewhere in between the polynomials and the formal power series. And for any formal power series, you can define this norm. Okay, it could be infinite, but you just take the L1 norm with these powers of R. And we're supposed to think of this as the functions on a disk of multi-radius R1 up to Rn. And now you take the norm finite elements of the formal power series. Okay, but now we want to see some kind of geometry within this disk. So suppose that multiplying by f is a strict monomorphism from this guy to itself. Then you can consider this complex in degrees -1 and 0. And the quotient, uh, you can now take the Gelfand spectrum or Berkovich spectrum. The quotient is going to cut out some subvariety of the disk defined by f equals 0. Okay, so for complex Banach algebras, the Gelfand spectrum is just the maximal ideal spectrum, and it's the same as the Berkovich spectrum. So we're cutting out some sublocus within the disk of radius r. You could also repeat this, you could now take another function and cut it down even further. Yeah, this picture is supposed to represent like a two variable thing, like f of zw equals 0 in the complex world. Okay, so here's some other important types of maps. The first one I'm denoting by these green bubbles, which are, so the black points are where some uh, thing in C of x over r is 0. So I've just defined it as a discrete set. I'm not sure if it can have like accumulation points. Probably it can, but let's just say it's represented by these 7 dots inside the disk. And we can add one variable, y over s, and then just mod out by y minus f. It's not a strict morphism, but it's still a morphism of Banach algebras over C. And what this represents, and I've written in green here, is the points where the absolute value of f is less than or equal to s. So it includes f equals 0 points, but it includes some neighborhood around them as well. And if you think, as Berkovich does, the point is actually the valuation. But if you think in terms of like complex analytic geometry, you're really taking points where the absolute value of f, evaluate at that point, is less than or equal to s. And you can do the opposite. You can take greater than or equal to s. So there you're still out of variable y over s, but now instead of modding out by y minus f, you mod out by fy minus 1. So I guess we've partitioned the disk into these two regions, one that's close to f equals 0 and one that's far away from the f equals 0. So these kind of regions are completely foreign to algebraic geometry. This is not, there's no way to define these things by like a finite number of polynomials. Okay. They look completely different than Zariski open or closed subsets. So I just want to emphasize that this red and this green region are like they don't look anything like something Zariski open or Zariski closed. It's something in between. But there are a lot of problems with this geometry. Um, First one is that, remember that all the localizations that I spoke about were flat. So this thing, sorry, so this thing is supposed to be representing some kind of disk of radius 1/2 inside a disk of radius 1. But the map is not flat with respect to this Banach algebra. In other words, this map, in other words, tensoring, maybe I should have written here. So, I mean, in other words, tensoring with this guy of radius 1/2 is not a flat, it's not flat as a functor from C of x modules to themselves. So in that sense, it doesn't seem to fit in with the story we told earlier about localizations and how you can define flatness in any symmetric monoidal category. This is not fitting in with the story at all. Now, instead of flatness, I can ask if it's a epimorphism in the category of rings. And that is true. So it is true that C of x goes to C of x over 1/2 is categorically an epimorphism. Here it's crucial that I'm not, epimorphisms of rings and modules have nothing to do with each other. So I'm not saying that it's an epimorphism of C of x modules. I'm saying it's an epimorphism of C of x algebras or of rings, of Banach rings. So that categorical epimorphism translates into this completed tensor product, but and that works. So the completed tensor product of this functions on the half radius disk is with itself is the half radius disk. So then you might think, okay, maybe I can define a topology using just epimorphisms. But that's not a good idea at all because there's way too many epimorphisms from C of x to R. For instance, you could just take something stupid like C of x goes to C. Wait, no, sorry. Yeah, that would also be an epimorphism where I just mod out by x. But that's clearly not has nothing to do with a cover. That would just be a single point in the middle of a disk. So that's not something we want at all. So,
Sorry, what are RAs?
sorry.
The R, what is that? I
Oh,
mean,
I'm sorry. I'm just it's some Banach ring. Um, so I'm saying there's too many epimorphisms from C of x to some Banach C algebra.
okay, okay, thank you.
So even though this map is an epimorphism, there's just too many strange epimorphisms that we don't want. Uh, for instance, just C of x goes to C itself would be an epimorphism, and this is not any kind of like disk. It's just a single point. So um, seems like there's too many things like that. So we can make the problem, we can demand a little bit more. We can demand the derived tensor product uh, of C of this thing with itself is itself. That's a stronger condition. It implies the previous condition, and we can ask if it's true. But the fact is, it's not even true. So this is related to the first de Rham cohomology or the cotangent complex of this thing being unmanageable. There's a long history of this reasons why this is a bad thing to consider. And in non-Archimedean geometry, it goes back to Grosse Clone. The other the reason that I tried to impose this stronger condition is based on work of Taylor and Putinar, and I'm sure many of you know that story relating homological epimorphisms to this Taylor spectrum and why uh, this is a nice condition to have, but it doesn't work in this condition. Now, Bambosi studied what's called overconvergent geometry, and I'm gonna talk later about how uh, this ring of overconvergent functions on the disk of radius R does have that property. But what we can do is we can take all functions inside here, which converge on a slightly larger radius. And that's going to give me a sub ring. And in fact, we're going to have four rings. And in classical functional analysis, people would consider this as a dual nuclear Frechet space. It's a certain kind of locally convex topological vector space. But instead, I'm going to discuss the Ind category, and we're going to view this as an object in Ind of Banach spaces over the field. And in fact, all four of these rings are Ind, like in a natural way, Ind Banach rings, and the morphisms are bounded morphisms of Ind Banach rings. They're just morphisms in the Ind category of Banach rings. Any questions before I dive into Ind? So I think before Prosmans and Schneiders discussed Ind, there was a long history of Husserl and other people talking about bornological vector spaces. So maybe at first bornological vector space was a type of topological vector space, but then it ended up being its own thing that doesn't, and then you could induce a topology from a Bornology, and you can induce, it's a very long, complicated story. Um, I should advertise Jack Kelly recently wrote a paper with two other authors in which they kind of compared some of the notions that I'm going to be talking about with the more classical notions of Bornologies. Anyway, Bornological vector spaces can also be thought of as a full subcategory of Ind Banach spaces. But I don't find that to be super helpful, that perspective. So anyway, Ind Ban is defined as a subcategory of all the functors from Ban to set. And in a second, I'll say more concretely what they are, but they are subfunctors for which f of v is a certain limit just of sets. And what is this VI? Well, VI are Banach spaces, and we're going to have a functor from a certain thing called a filtered category that sends I to VI. But you can just think of objects as in Ind Ban as this formal filtered colimit. So as an example, if I have C of X over 1 plus a half, restricting down to C of X over 1 plus a third. So this is like a radius 1.5, radius 1 1/3, and I just keep on going. These are all injections, and I take the union. I just consider this system in a formal way. That's one of these formal colimits. And you can easily see that, okay, the amazing thing is that this category now has all colimits is kind of obvious, but it has all limits also. And I'll discuss that in a second. But this is a complete and co-complete category. It has all, and its filtered colimits are exact. Um, and the way you compute HOMs between two of these is you take the co-limit over J of, and then you take the limit over I of that. And tensor products, I mean, just in the abstract sense, there's these very simple formulas for what is the tensor product, what is the internal Hom. So you extend this whole closed monoidal, closed symmetric model structure to the Ind category. So as I said, like the categorical limits are very easy to write down. We already gave examples of how to think of like typical dual Frechet space in terms of this. But what about we want a category that's kind of big enough to have all the objects of functional analysis. So how do I think of Frechet spaces? Well, I told you that this category was closed under limits. So a Frechet space should be kind of categorically a limit. Um, so we want maybe to understand something like this, say a sequential limit. But we better first understand products before we can understand limits. So what about a countable product of Banach spaces? How do I think of, how can I realize that inside Ind-Ban, which has limits for some very abstract reason? Um, so as a as a preliminary step, I'm going to discuss the products in the contracting category. The contracting category has the same objects as Ban, but it has different morphisms where their operator norm is less than or equal to 1. So it turns out that the product of Banach spaces is just the usual L infinity thing, which is you take sequences with bounded supremum. Now I'm going to define this post set of functions from I to n. So suppose I'm given a Banach space for each I in some countable infinite set. I consider all functions from I into n. Now I was countable, but these functions form an uncountable set. And they have a partial order, which says that psi1 is less than or equal to psi2 if its values are just less than or equal to. And following work of Ralph Mayer, I showed with Kobe Krimlitzer that this product of VI is in a very explicit way an object of Ind-Ban. It's a co-limit of these L infinity spaces where I've done this trick of weighing the norms on them by this inverse psi I. So literally psi I is a natural number. I mean, of course, bigger than 0. And you just take its inverse and you weigh the norm on VI by that guy. And then you take this soup norm on those, you get some Banach spaces. And then you take this, so it turns out that you get maps between them. So maybe I'll write it in a different color. There are maps from, so if psi1 is less than or equal to psi2, you get a map from 2 sorry, this is psi1 and this is like the thing for psi1 and this is psi2i inverse. So you get maps that relate the different size. You take this formal co-limit and that fills out the product of VIs. In this case, the product at Ind-Ban is Aleph1 metrizable. It's a technical condition on an object in Ind-Ban. I don't think it's worth to say the exact definition, but it turns out to be equivalent just with that when you tensor V with a product, that it filters through the product. So maybe I'll write that over here. So V tensor product of Wi is the product of the tensor Wi. Now, in algebraic geometry, this never happens unless V is finite dimensional. So the amazing thing is that in in algebra this never happens, but in this Banach algebra it does happen. This thing will always commute. And in fact, for any countable sets I and j, and if Vi and Wi are Banach spaces, products just commute with tensor products in this sense. So these Aleph-1 metrizable objects are closed under countable limits, co-limits, and tensor products. And now we'll define another. So this might look a little bit funny that I'm defining what a nuclear map is, because, I mean, these are well-known definitions in topological vector spaces, but a lot of this story, it works over any Banach ring, so not just a field. And for that reason, I prefer this definition. You say that an element in Ind-Ban is nuclear if for all Banach spaces, here it's crucial that I didn't say that W is not an Ind-Banach space, just a Banach space, that the dual tensor V is isomorphic to the internal Hom from W to V. So this should remind you of, well, if I just have a map between Banach spaces, I mean, a map between Banach spaces is nuclear if it comes from, so this should remind you of the fact that you always have a map from this to Hom. But not every Hom comes from this thing. So not every Hom is trace class. And if it is, you call it nuclear. So I'm not defining a map to be nuclear now. I'm defining an object in Ind-Ban to be nuclear, if this holds. And you get this interesting subcategory. And the nice thing about this subcategory is mapping into a nuclear object is always representable by this collection of trace class maps. So for every F, there exists a J such that to give you a map between to specify what F is, I just fix J to be J of F and define for you trace class maps from all Vi into that Wj that are compatible. Okay, so these nuclear objects, they have this abstract definition, but you can also think of them as just co-limits along this sequence of trace class morphisms. So I have my abstract co-limits, let's say, for instance, V2, V1. Sorry, that's the wrong way around. I have my abstract co-limit, say, V1, V2, dot, dot, dot. And each of those maps is trace class map of Banach spaces. That will define for me a nuclear Banach space and every nuclear, so a nuclear Ind-Banach space, and every nuclear Ind-Banach space comes about that way. And this category of nuclear Ind-Banach spaces is closed under tensor product, under countable products, and all coproducts. And the real reason that I always needed nuclear objects is because it's basically the only way I knew to prove that something was flat over the field. So this is a very funny situation because a lot of times you don't want the homological algebra over the field to play any role, but then you worry that it might. But if you have a nuclear object, it's flat over the field, so you can ignore the homological algebra of the field just like you do in algebraic geometry. So it's great to be able to work with nuclear objects for that reason. I should say that a Banach space itself is never uh, is only nuclear in this definition if it's finite dimensional. So nuclear objects are really something that's interesting for Ind-Bahn. So if I have a Banach algebra, I don't know whether it's flat or not. I have no way to check whether it's flat or not. But if I have an Ind-Banach algebra, as long as it's nuclear, it's flat. And finally, there's some 2 out of 3 things for nuclear. For instance, if you have a strict short exact sequence, and if the outer terms are nuclear, then so is the inner term. Maybe I'll pause for questions. Sorry, it's a little bit technical, but in a second I'll get to a concrete, maybe it's a question for the audience.
I'm
Um,
sorry, I skipped the tensoring there in your category. When you define, it was your definition, right? Getting the as a co-limit of the tensoring of the
yeah,
components.
yeah, the tensor product basically extends. So tensor products, they look like this in the int bond category.
Yes, yeah, this one. So this one you accept like a definition, is it? Like extension. So
Um,
it's not a property here.
yeah, it's okay. So um, I think you have to take one of these two as a definition and prove that the other one is the adjoint functor to the one that you take as a definition. But you have to take at least one of them as a definition.
Okay, okay. Yes.
What am I saying?
Okay, okay. Okay, yes, I got it.
I mean, there may be a more abstract way to define it that doesn't use a presentation, which would be better because if I define it this way, I have to prove that it doesn't depend on the presentation. So I should emphasize that there's nothing canonical about a presentation. Like for any object in Ind-Bahn, you can write it in many different ways as a as some co-limit.
Yeah,
There's no there the I mean there's an equivalence class and the 2 ways are equal if this functor is equal. So there's nothing canonical about the way you present it as a co-limit, and for that reason, these definitions you have to then check that it doesn't depend on the presentation. Um, I'm blanking out a little bit, but there might be. I mean, okay. For instance, I mean, this definition is kind of canonical, and then this one is you just prove that it's an adjoint. I mean, this definition, these are called internal natural transformations of functors. So when you're doing enriched category theory, um, you can just simply take your functors and define natural transformations between them. And
yeah,
there's an enriched setting here where the Homs are naturally themselves Banach spaces, whatever. Or so this definition kind of you can check that this holds.
yeah. Okay, good.
In
Thank
other
you.
words, the left-hand side is kind of defined in a canonical way, and you can check that this equality holds, and then you can check that this one gives the adjoint functor, which is then unique up to natural isomorphism,
Yeah, okay, thank you. Mhm.
and therefore doesn't depend on the choice. So there's some better ways to do this. Um, okay, so I'm just gonna do a quick one more formal property that using this presentation of the product, we were able to prove that the dual of the product is the coproduct of the duals. So the easy, uh, the easy statement, the almost completely obvious statement, is that the dual of the WIs will be the product of the WI duals. But the less obvious statement, less obvious, is this one. And in a similar way, the dual of a limit of Banach spaces is the formal co-limit of the duals of those Banach spaces. So now I wanted to return to the kind of star of the show, which is this overconvergent disk. Obviously, it's an object in Ind-Bahn. It's even an Ind system of algebras and algebra maps, but it's obviously an algebra object in Ind-Bahn. So it's nuclear because it's easy to show that the transition maps are trace class and satisfies this homological epimorphism, or oh, I call it homotopy epimorphism property, which is that the completed derived tensor product of it with itself over, say, the polynomials is just, you just get back the thing you started with. So there's no, um, so it's, we think of this as a derived intersection of this disk with itself. And it does work. And if I remove the dagger, it's not true. So here I'm thinking of the polynomials also as an Ind-Bahn algebra. It's just the co-limit of polynomials of finite degree. So it's also an Ind-Bahn algebra. And that's what I'm tensoring over. So in my abstract, I talked about Prosman and Schneiders' work. So they showed that this Ind-Bahn category has all the properties of Ind-Bahn, but now it's closed under limits and co-limits, and filtered co-limits are exact. It's a closed symmetric monoidal quasi-abelian category with enough projectives and some more nice properties. And they also developed a sheaf theory for Ind-Bahn sheaves on topological manifolds. And there's a lot of reasons to think that their approach is very nice for proving duality theorems, although somehow nobody really picked up. I mean, they stopped working completely, and almost nobody picked it up. Me with my collaborators, we did a little bit of their work, but we kind of worked over any Banach ring, and that makes it harder to proceed. But somebody should have just picked up where they left off and worked over the complex numbers, but nobody did. And I feel like their work is great for proving some certain duality theorems, like Poincaré duality. Um, Ishimura's theorem on a complex manifold says that the analytic differential operators, which are kind of, include kind of differential operators of infinite order in a certain sense. I can talk more about that maybe if we have time. They prove that the analytic differential operators are the endomorphisms of the structure sheaf. So a differential operator acts on the structure sheaf in a C-linear way. Here, I mean like on a complex manifold, and it's just the sheaf of holomorphic functions. But we consider it as a sheaf of Ind-Bahn spaces over X. And so Prosman and Schneiders, I mean, they proved this, and they even proved it for the derived endomorphisms. But both sides are kind of Fréchet sheaves, but thought of in Ind-Bahn. So I can just quickly say why Fréchet. So the right-hand side is Fréchet just because if I have an open set in X, I can restrict the cotangent bundle of X to that open set. Let's say T star X restricted to U. And the symbol map of the differential operator is a function on the cotangent space. And the fibers of the cotangent space are Stein manifolds. And we know that like functions on a Stein manifold are an increasing union of compacts, of functions on the compact. So we're intersecting the functions on this increasing union where the compact spaces are exhausting the fiber direction. And that's why the right-hand side is basically why it's Fréchet. So what I'm trying to say is that the symbol of a differential operator, um, like in local coordinates, um, it's sort of, I mean, it sort of lives in U U cross A1. And for that reason, like you're getting sort of a Frechet algebra because you can exhaust A1 by compacts. And it's kind of funny because the Frechet structure on the left-hand side, it comes from sheaf theory because you have to sheafify the endomorphism. So whenever you talk about endomorphisms of a sheaf, you need to take the pre-sheaf and O of U and sheafify it, but then it's a limit over all covers. So again, you get a Frechet structure in the limit. So the amazing thing is that these Frechet structures match, and Ishimura's theorem, um, he proved it in a long time ago. So, but I looked at it in the rigid analytic context with Ardakov, and we kind of proved it in what I think is a better way. And we could have sort of done that in the complex situation, but anyway, Prosmans and Schneiders they set up this theory and they used it to prove theorems like this. Um, so just to end the talk, I want to talk about a kind of duality that goes back to Grothendieck and other people. And it basically says if you have P1, then functions on one hemisphere or even one lump of P1 are dual to the functions on the complementary lump. Um, I forgot all the names of the people that worked on it, but I'm looking at a very easy case of it and trying to address it in the Ind-Banach world. So just like the polynomials are an Ind-Ban algebra in a natural way, so are the formal power series. Um, so it's just a product there in Ind-Ban. And let's define this Frechet type algebra as a limit of functions on smaller disks. Okay, so uh, the fact is that you again get a homotopy epimorphism. Um, that's the first thing. Second of all, this Frechet type algebra in Indban is nuclear. Now we have the Hadamard product, which takes two formal power series and just sums up their coefficients. Of course, it's not defined always, but the nice thing is it gives maps from the functions on this open disk to the functions on the overconvergent disk of the complementary radius. And it gives functions on the overconvergent disk of some radius to the functions on the open disk of the complementary radius. So complementary, I just mean radius r is complementary to radius 1 over r. And these maps are both isomorphisms in Ind-Ban. So where I got stuck, and maybe I'll leave that as an open question. So, so each of these guys is dual one to the other. But what about the derived duals? So there's something that really traumatized me because this whole story worked so beautifully until I had to compute this derived dual. And I'd like to say that these guys are derived dual to one another. And I'd like to say that the derived dual is just the same as the underived dual. But when you're dealing with the dual of something that's already like written as a limit, I just I just was unable to compute it. I think actually going back to the work of Prosmans and Schneiders, I know how to do this now over the complex numbers, but I was trying to do it in some level of generality, and I just wasn't able to solve it. And I will stop there. Thank you very much for your time.
Thank you. Thank you very much. Are there any questions or remarks?
Well, I have a question concerning homotopy epimorphism that you have just mentioned for your algebra. Um, can you show us, please? I mean, the problem with the previous slide, right?
Yeah.
Well, maybe I'm mixing up something here, but is the property like homological epimorphism, like localization, like polynomials into algebra is a localization? Is it the same property in your category?
Yeah, yeah, it's exactly the same. I
Oh,
just called
okay.
it, yeah.
Oh, so the same was for f of x into disk algebra, right?
For the overconvergent disk it works, but for the disk algebra it doesn't work.
Ah, okay, okay. Yes, yes. So, but what about several variables?
Oh,
You said,
all of these properties hold in several variables because you just need to tensor together the algebras in one variable to
okay,
get the
okay.
several variables. So uh, I have an article with Mukherjee, uh, and we justified the several variable case as well. But all, I mean, the poly disk or disk with multi-radius R1 to Rn is just the tensor product, completed tensor product of the disks of radius of n different disk algebras. So
Yes.
in all the different kinds, so in all the different things we're talking about, you have the properties like this, for instance. For instance, for the formal power series, which is kind of an infinitesimal disk, uh, you have this relationship, and same thing for the overconvergent disks, and same thing for these Frichet-Stein open disks.
Okay, okay. So if you choose just the formal power series is again embedding of polynomials to formal power series is also localization,
Is
right?
also, yes, absolutely. Yeah.
And it stands for,
So
yeah,
in my initial sequence, um, everything in sight it would be a localization. So, oh, I think it was before this. So all of these are localizations, and you can also put the open disk uh, um, in the correct place, and it will also be. I mean, you can also stick that in. All the inclusions are localizations, but I don't like to call them localizations because I mean they're localizations in the categorical sense, but not in the algebraic sense.
sure, sure. Okay, okay. Okay, yeah, thank you. And then maybe the last question. So do you have something like non-commutative examples? Like you have a non-commutative algebras, and in your category you can see that is a look, it's
Well,
like
I
a
actually like
localization.
I'll just I want to mention two things in relation to the non-commutative world. So the amazing thing is that well, first I want to say like a work of Kontsevich on differential graded algebras, but not necessarily commutative. Um, and so here we use homotopy epis. The second is that push out of so, okay. So if I do I don't even know what the correct notation for it would be, but um, there's a theorem that if R and T are commutative, this is a theorem of Lazarev, I think, and someone else. If R and T are commutative, um, then you can do these kind of push outs in the either with the free product of algebras or the um, usual commutative tensor product of algebras, and the relationship is actually the same. So I'm not saying in any way that these things are the same. These have nothing to do with each other, but this homotopy or homological epimorphism property, it it can be used in non-commutative geometry without changing the content if everything is commutative. And then finally, like there's work of Bambosi and one other guy, I forgot his name, um, that uses notion A, let's say this is notion A, to get a space associated to a non-commutative ring, which is something that always people said is impossible to do because non-commutative geometry is supposed to be like kind of non-local. But anyway, they do have something interesting. They have a Morita invariant notion of getting a space associated to a non-commutative ring. And basically they construct a kind of topology out of these non-commutative homotopy epis, whatever they are, which is notion A, which if things were commutative would agree with notion B. And they construct a growth entity topology, and then from there there's a kind of general machine due to Johnstone and topos theorists for getting a space. And then they get a space and they're actually able to compute it for some simple non-commutative rings. So these are the three things like I know of in the non-commutative world. And then of course there's work of Alexei Alexei, what was the name of the other guy? Oleg or Apisov?
Oleg Aristov.
Oleg Alistov and Alexei have done a lot of things with like universal enveloping algebras, and they've studied the homological epimorphisms there, and so there is a lot of work in the non-commutative situation as well.
Yeah, okay, thank you.
More questions, please. Well, I
I
have
should say, I just say one thing, like in the Kontsevich work, like he just is saying that the derived category of B is fully faithfully embedded in the derived category of A. I mean, that's his notion.
hmm. I also have a question, one more question about homotopy epimorphisms. So you said that the inclusion of polynomials in homomorphic functions on the disk is homotopy epimorphism in the setting of, in your setting, I mean, in the setting of int Banach spaces, and the same for the polydisk. So the question is, have you considered other types of domains, like, for example, the ball in the two-dimensional ball or something like that?
I expect it to also hold.
Mm.
The only, yeah, I expect so. So we have a theorem, we have a theorem, but it's a little bit hard to say exactly. But I think like any convex Stein will give will be a homological epimorphism. I mean Stein open.
Hmm. Mhm.
So, but the proof is somehow super technical. I mean I definitely expect the ball to work and all those things to work. Um, but I don't remember even how we proved it. So I usually just studied disks because
Mhm.
They break up under tensor product very nicely, unlike the ball. But yeah, I don't remember. We have this paper Stein domains in which I believe we proved
Mm.
that it works. So maybe I should say one last thing. So in a lot of kinds of geometry, um, like the open maps from whatever kind of spectrum you're talking about, between uh, nice A and B, where nice means like, for instance, aphanoid in the rigid sense, or Stein, which means O of whatever it is, convex, open, modulo, and ideal, uh, etc., um, are in one-to-one correspondence with just homotopy epimorphisms. So we checked this in the alphanoid case over a non-Archimedean field or over a Stein, and like open means like in the Stein case just in the classical topology.
Mhm.
So once you fix the algebras, I claim that any of the maps you're talking about, like a ball inside Cn or anything like that, will always satisfy the homotopy epi property.
Mhm. Okay, thank you. Well, maybe one last question from me is that again about homotopy epimorphisms. So in your case, you define an exact structure on the category of modules by using strict maps.
Mhm.
Another option is to consider a different type of admissibility. So we say that, um, um, for example, an epimorphism is strict if it is a retraction in the category of spaces, and a complex is admissible if it splits as a complex of topological vector spaces, or in your case, of Banach spaces. Have you tried to consider this different exact structure? So, because in the setting of Frege algebras, it leads to uh, another class of homotopy epimorphisms, which is smaller than homotopy epimorphisms in your sense. And in the
Um,
terminology of Joseph Taylor, they are called absolute localizations. If here we also have a problem of determining homotopy epimorphism between algebras of holomorphic functions. And in this case, we still don't know how about the inclusion of polynomials of two variables in the algebra of holomorphic functions on the ball, on the two-dimensional ball. So if you take polydisks, for example, then it will be a homotopy epimorphism in this strong sense. But if we replace the polydisk by the ball, it's still an open problem. What happens if we consider the embedding of polynomials into the homomorphic functions on the ball? So it is a homotopy epimorphism in the weak sense, but we don't know about this property in the strong sense. So my question is,
yeah.
does it make sense to consider this stronger property in the setting of in the Banach spaces?
I think so. I never considered it, but I think it does make sense.
Mhm.
But um, you know, all of the Ind properties just are induced from the properties in Bond. So usually say that a morphism in Ind Bond is strict if it can be written as a co-limit of strict morphisms in Bond. But it sounds like the notion you're talking about would change the strictness even for maps between Banach spaces. So it's actually, yeah, it's a very interesting question. But I don't know anything about it. But I know that Ralph Mayer considered this type of exact structure or something similar. And it sounds like it makes some things easier and some things harder. So
Yeah. Mhm.
yeah, I don't know.
Yeah.
But
Okay, thank you.
my problem was always the thing that where I ran into trouble was always like I don't even know if this is injective in Ind-Bahn in I don't even know if the field itself is injective in Ind-Bahn. It's injective in Bahn, but I don't know if it's injective in Ind-Bahn. And if it were injective in Ind-Bahn, I wouldn't have this problem. But it seems to probably not be. So it's kind of a mess right now. And
Mhm.
some people told me that this dual even depends on your model of your axioms of mathematics. I mean, this derived dual. But anyway,
Okay, thank you.
yeah, thanks very much. It was great to meet everybody, and
Mhm. Any
thank you
other
very much.
questions? No? Okay, thank you, Oren. Thank you very much
Okay,
for the very interesting talk.
okay,
Take
take
care.
care.
Yeah,
Bye.
that's an interesting talk.
Thank
Same
you.
here. Bye.
Bye. Good night.